You ever see a stealth jet and wonder how a huge, screaming piece of metal can just vanish from radar? Well, it's not magic. It's an incredible feat of engineering, and it's all about solving one of the toughest puzzles in aviation. So let's get into it. Okay, check this out. This is a modern UAV, an unmanned aerial vehicle. And you can see its whole shape is designed to be smooth, flat, what they call low observable or stealthy. But you know what the biggest radar target on an aircraft is? It's not the body. It's what's buried deep inside, the engine. So that's the million-dollar question, right? How in the world do you hide those spinning metal fan blades, one of the most radar-reflective parts of the entire plane, from an enemy that's actively looking for you? Well, the answer is pretty ingenious. You do it with this thing, the S-shaped inlet. It's basically just a winding, snake-like air duct. This clever, curvy path physically blocks radar waves. They can't go straight in, hit the engine, and bounce straight back out. It's a fantastic way to hide in plain sight. But this brilliant fix creates a whole new massive headache for engineers. And here it is. This is the core conflict. For a jet engine to get maximum power, it needs a smooth, straight shot of air. Think of drinking through a perfectly straight straw. Easy, right? But for stealth, you need that path to be as twisted as possible to block radar. These two goals are basically at war with each other, and trying to find the perfect compromise is, well, unbelievably hard. So what makes finding that perfect sweet spot so difficult? It really comes down to just the mind-boggling complexity of it all and the sheer number of things you have to get right. To even begin to define the shape of this S-curve, engineers started with 11 different variables. That's like having 11 different knobs to turn, adjusting the curve here, the width there, the height, and every tiny little tweak can have a huge effect on both the airflow and the stealth. Now, here's the wall they hit. If you wanted to test every single possible combination of those 11 variables using the best, most accurate computer simulations, it would be almost impossible. We're talking about an insane amount of time and money. You could tie up a supercomputer for months, maybe even years. So they needed a better way, a smarter way. And this is where things get really clever. This is the big breakthrough. A team of researchers came up with a much more intelligent approach to the problem by breaking it down into a really efficient process. Here's their game plan in 3 steps. First, simplify. Figure out which of those 11 knobs don't really do much and just get rid of them. Second, build a smart, predictive model that's both fast and accurate. And third, unleash a powerful algorithm to go hunt for the best possible designs. So, step 1, simplify. They ran what's called a sensitivity analysis to see which variables actually mattered. And you see those little bars on the chart for Y1, A4, and B4? They barely make a difference. So they just got rid of them. And just like that, an 11-variable problem became a much more manageable 8-variable problem. For step 2, they built something called a co-Kriging surrogate model. Now, that sounds complicated, but think of it like this. Instead of paying for 1,000 super expensive, perfect oil paintings, you pay for 10, and then you use thousands of cheap pencil sketches to accurately fill in all the details in between. By mixing a few high-cost, super accurate simulations with tons of low-cost, less accurate ones, they got a model that was the best of both worlds, incredibly fast and surprisingly accurate. So now they had a simpler problem and a super efficient model. They were ready to find the one perfect design. Except what they found wasn't just one design. It was something way, way better. This right here, this is the aha moment. It's called the Pareto front. Instead of finding a single point that said this is the best inlet, the algorithm gave them this entire curve of optimal solutions. Every single point on this line is a top-tier design. It represents a perfect trade-off where you can't make the stealth any better without sacrificing a tiny bit of engine performance, and vice versa. It's not one answer, it's a whole family of elite choices. So, from this family of champions, the team picked out 3 different personalities to look at more closely. There was Inlet A, the specialist that prioritized stealth over everything else. Then there was Inlet C, the powerhouse that was all about raw aerodynamic performance. And right in the middle, you had Inlet B, the balanced all-rounder, trying to give them the best of both worlds. All right, now for the moment of truth. How did these new, optimized designs actually stack up against the original inlet they were trying to improve? Well, the results were pretty spectacular. The numbers don't lie. Just look at PR, or pressure recovery. That's a measure of how good the airflow is to the engine. So higher is better. The original was sitting at about 0.92, but look at the all-rounder, Inlet B. It jumped all the way up to 0.97. Now look at DC, or flow distortion. This is bad, turbulent air, so you want this number to be as low as possible. The original was a pretty high 0.37. Inlet C got it down to an unbelievable 0.003. I mean, these aren't small improvements. This is a giant leap forward. And you can literally see the changes right here. The solid blue line on the left, that's the path the air took in the original design. The dashed lines on the right are the new optimized paths. You can see how Inlet A, the stealthy one, has that sharper initial curve to do a better job blocking radar. The others are just subtly reshaped for smoother airflow. This 3D view makes it even more obvious. The gray shape is the new optimized Inlet B. That faint blue outline, that's the original. You can see how the new design is wider and has a more gradual, smoother curve in just the right places, all figured out by the algorithm to feed the engine cleaner, more stable air. You know, the researchers themselves really said it best in their paper. Their method didn't just work. It was incredibly effective, creating designs that were way better across the board. Better airflow, less turbulence, and better stealth, all found with this super efficient process. And that really leaves us with one final big question. This whole approach, this smarter way of designing, solved a huge problem in aerospace engineering, but its potential is so much bigger than just that. So if this method can so dramatically improve a stealth jet inlet, what other huge complex design challenges in medicine or energy or anything else is it about to solve next?